Welcome back. Today we're going to be talking about plate tectonics, and over the next couple of weeks we're going to talk about the inside of the earth and what we can observe on the outside, and then we're going to come up with a plan on a theory on how we can explain how the inside of the earth leads us to those observations on the outside. And the theory of plate tectonics is a pretty powerful unifying theory. To start off with, we're going to learn about the Earth's interior. Today, I would like you to read pages 124 to 131. Be looking for these key terms: seismic waves, which are also earthquake waves, crust, the mantle, the inner core, the outer core, and then two rocks, basalt and granite. Maybe those are new terms. We're going to look at the characteristics of the layers and then put kind of our ideas of our understanding of the inside of the Earth into eventually an explanation for what we see on the outside. The inside of the Earth, we can get a look at the outside of the Earth, you know, the rocks on the surface, but how do we know about the inside of the Earth? We have direct evidence from mine shafts going down a mile and a half, 2 miles, and even further than that through core drilling, where they take a drill bit and drill down into the earth and then pull out the core, and we can look at it. This isn't from the earth, this is a piece of concrete, but this is a core sample from underneath my feet right now, from the Calumet and Hecla mining operation. Because this area was mined so extensively, we have a pretty thorough understanding of the layers underneath our feet. And the core drilling goes down about 8 miles. The deepest cores have come from the ocean. Underneath the ocean, the crust is thinner, so they thought they could, and also because of the depth of the water, you get kind of a couple of miles of drilling for free with no work involved. You just lower the bit down. And so they drilled, even though it would be hard to keep the ship stable and all of that, they drilled in the Pacific down about 8 miles. And you know what they found at those depths? Rocks are pretty much the same as they are on the surface. Less weathered, of course, because they're not exposed to air, but pretty much the same. Deeper than that, we can't go there. The pressures inside the earth, the temperatures inside the earth are such that we can't go into the earth. Even at the bottom of the Quincy mine, the temperatures were in the 90s every day. Even if it was below zero outside, temperatures inside were in the 90s. But we do have some indirect evidence about the inside of the earth. This is direct evidence. I can put my hands on this rock, and I can put my hands, this rock might have been a mile below the surface. This is a piece of mine rock from the Calumet and Hecla Mining Company. So this could have been 100 years ago, it could have been a mile beneath the surface, and I have direct evidence of that. These miners saw those rocks and brought them to the surface. Deeper than that, sometimes the inside of the earth comes to us, and it spews out of the ground as well, it's magma when it's below the ground. When it comes up, it's called lava. On Kilauea in Hawaii right now, the lava's been flowing out for seems like forever. Every day, if you follow that in the news, there's new lava flowing out all the time. So that's giving us an indication, a snapshot of what's inside the earth, down deeper than we can mine or drill. But still, that's direct evidence. We can put our hands on it. You better wear gloves, but you can put your hands on that. And I messed it up. Deeper than that, we have to rely on indirect evidence. What's underneath the magma? It doesn't come to us, we can't go to it, so we have to rely on indirect evidence. And I want to take a look at this. This is a kind of pretend this is a cross section of the earth. Earthquake waves, when an earthquake goes off, it sends out waves in all directions. And there's a couple of kinds of earthquake waves. There's primary waves, which are like this. They're kind of a compression wave. The ground moves back and forth. And then there's a secondary wave that moves, you know, kind of side to side, like that. And they behave a little bit differently, and we can use that. Primary waves, it turns out, can't go through liquids. So when this earthquake goes off, it sends out waves in all directions. Let's say these are the P waves. And all around the earth, if you're here, anywhere along here, your seismograph can detect those P waves. But not if you're here, or here. There must be something stopping the primary wave from getting to the other side of the earth. Well, primary waves can't go through a liquid. So there must be a liquid layer inside the earth. This is called the P wave shadow. And if the earthquake was over here, then the shadow would be over here. And if the earthquake was down here, then the shadow would be up here. And so by plotting that over thousands of earthquakes, they have hypothesized that at least part of the core of the earth must be liquid, because that would explain why there are no P waves in that shadow zone. That's part of the story. The S waves from an earthquake, they're not quite as fast as the primary waves, and we'll talk about how we can use that later. But the S waves, they go through liquids. They slow down because a lot of waves, when they go from a solid to a liquid, they slow down. Sound waves travel like 4,500 meters per second in a solid, and only about 1,400 meters per second in a liquid, and only about 340 meters per second in a gas like air. But anyway, so when they were timing these S waves, I'll change colors for the S waves, they found that if it was an S wave should be going fast, slow down through the liquid, and then speed up again when it goes through the solid on the other side. And there should be a time. You should be able to time it and calculate, you know, how fast it would have gone through the different layers. And so it gets there on time, you know. They found out that between here and here, the S waves were getting to the other side of the earth quicker than they calculated. So there must be something else going on. And they decided that if this was a solid, then those S waves would be going faster, slow down through the liquid, speed up again in the solid, slow down through the liquid, speed up again through the solid. And using that model, the waves arrived right on time. So from all of this indirect evidence from earthquake waves, even though we've never been there and we really can't go there, they have determined that this outer layer, the outer core, is a liquid, and the inner core is a solid. Pretty cool that we can do that without ever having gone there. Now is it exact? Well, we may tweak it if we find out more information, but this fits our observations, even though it's indirect evidence. So from all of that, from putting all of this evidence we have, the direct evidence from mine shafts and core drilling and lava flows, and the indirect evidence from seismic waves, we put this together as our understanding of the inside of the earth. The earth is made up of a crust, which is solid rock and relatively thin, maybe 50 miles thick. There's two kinds of crust. There's lighter continental crust. This is the rock that mostly makes up the continents. Now there's hundreds of kinds of rocks, so it's not entirely, just because it's a continent doesn't mean it's made out of granite, but granite is the most common rock of the continents. It's lighter colored because it has a lot of silica in it. In contrast to the ocean floors, are made up mostly of this basalt rock, which is darker colored. Even more important than the color is that the ocean crust is more dense than the continental crust. And because of that, whenever these two collide, the ocean crust always gets pushed under. And that's important for plate tectonics. Ocean crusts are made out of this lighter, less dense continental crust called granite. Take it for granted. And ocean floors are made up of this darker colored, denser, heavier rock called basalt. That becomes important later on, so we have to get this distinction straight. Underneath the crust is this mantle, which is technically a solid, but it flows. It's like pudding or like jello. It's magma. I mean, you've seen it when it comes out as lava out of a volcano. It's thick, and some of it is thinner than others, and that determines what kind of volcanoes you have and what kind of rocks you have. But it's like a pudding. It's technically a solid, but it still flows, and those flows are going to become important later on. Inside that is a liquid outer core and a solid inner core. Now keep in mind that as you go down, temperatures get hotter, and at this level it gets so hot that it's a liquid, even though the mantle was a solid. Here it's a liquid because it's so hot. As you get further down, it gets hotter. So the inner core is actually hotter, but there's so much pressure on it that even though it's hot enough for that to be a liquid, the pressure keeps it a solid. The molecules just can't move far enough apart to become a liquid. So even though it gets hotter as you go down, pressure increases, so that fine line between being a liquid and a solid. Here it's hot enough to be a liquid, but the pressure isn't so great that it makes it a solid. Here it's hot enough that it could be a liquid, but the pressure is so great it doesn't allow it to be a liquid. So read those pages. I think there's a set of questions for you to answer. Have a good day.